Welcome to today's MeKo MedTech Materials webinar about developing next-gen bioresorbable scaffolds in cooperation with Zeus. My name is Laura Denzer. I'm one of the project managers at MeKo and will be part of the speaker team today. We will give you a short overview of the two companies and then focus on the production processes of oriented polymer tubing and its way to a final implant. The webinar will take about 50 minutes, and due to the time difference of the US and Germany, it is pre-recorded. We still invited you to a live meeting today to give you a platform for your questions. Please send us your questions and write them down in the question area. We're going to answer all questions in personal messages or in the later uploaded video. The slides will be available on our website. Let's have a look at the presenters today. First, it's me. My name is Laura Denzer, and after my master's studies in engineering about different production technologies, I started my industrial career as a project manager at MeKo Manufacturing with the responsibility for new customer projects and their realization at MeKo. Fridtjof Strass works with MeKo for 4 years and is taking care of a variety of customer projects with bioabsorbable medical devices. He prepared, monitored and evaluated the case study about the optimizations of the new Absorv XSE for laser cutting at MeKo. James Lindsay played a leading role in the invention of Absorv XSE as well as many other bioabsorbable products. He has led Zeus Bioabsorbable Technology Group for the last 15 years on a mission to enable innovation and advanced medical technology across many disciplines. Wayne Black is currently the Global Product Marketing Manager for permanent implantable products at Zeus. He has over 18 years of experience strategically driving innovations in various markets, including medical devices. Zeus and MeKo have been working together for a long time, not only in the marketing for the new Absorv XSE. But now you might ask yourself, what is the potential overlap in the operations of Zeus and MeKo? Both are high-tech manufacturers with the goal of offering accurately processed products to their customers. Zeus is the specialist for the raw material for BRS. They are offering oriented polymer tubing with a high straightness and small wall thickness tolerances. Using the Zeus polymer tubing, MeKo is able to produce bioabsorbable scaffolds by precise laser cutting and achieving tight strut thickness tolerances of the final scaffolds. Me and Wayne are going to present the companies now, and afterwards James and Fridtjof will take over with the technical parts about the uniformity and orientation and their importance for design success and the manufacturing of BRS itself. All right, for the next 5 minutes I will give you a general overview of MeKo Manufacturing. Clemens Meyer-Kobbe started MeKo Manufacturing in 1991 as a one-man job shop. Here you see the present company building and how it evolved over the past 25 years. The last expansion is the part on the right side where the most of our production departments for nitinol components are located. And the planning for the next buildings are already ongoing so that we will have even more production capacity in the near future. Today, as you can see here, we have more than 300 qualified employees who are working in the laser material processing and related post-processes, as some of you might already know. Our focus is always on high precision and challenging processes, which we perform 24/7. Let's go through the general production process, which is performed according to our ISO 13485 certified quality management. The first step is the laser cutting. We also offer laser drilling and laser welding. In all those processes, we perform an in-process quality control, which allows us to achieve a superior dimensional accuracy. As a following step, we are able to heat treat or shape set your medical device. Of course, it always depends on the material which process we apply. A lot of medical devices need to be electropolished. Our machines allow us a widely adjustable range of material removal. For the subsequent passivation, we use an automated cleaning line to reach consistent results and to enhance the biocompatibility of the components. Finally, each part needs to pass quality control. We perform a 100% visual inspection of all implants and own several different automatic microscopes for further controls. Now, I would like to hand over to Wayne for the presentation of Zeus.
Thank you, Laura, for that great introduction. Hello, everyone, and welcome to our webinar on why uniformity and orientation are critical for design success. I'm Wayne Black, Global Product Marketing Manager for our implantable products at Zeus. Today, we have a new innocation session planned. Innocation may be a new word for some of those in our audience, but don't worry, we hear right after this webinar it's going to be added to the Urban Dictionary. Innocation is really a blend of our latest innovations here at Zeus with education from one of our premier senior researchers. But before we jump into some great details, here's a little bit about Zeus. Zeus has grown phenomenally since our founding in the 1960s, and we're growing faster than ever today. With over 2,400 global team members, we serve over 180 countries around the world and continue to be known for three big things in the medical device community. One, precision; two, quality; and last but not least, growth through innovations. These innovations are created worldwide. Our facilities span the Americas, Europe, and Asia Pacific. As you can see, we continue to be committed to growth, and some of the latest expansions allow us to keep that growth going. In the spirit of our founder, Frank Tourville Sr., our motto at Zeus has always been, "There is no good enough in true craftsmanship." With that motto, we continue to deliver products that help medical designers create new potential life-saving devices, matching our mission to enhance lives. Today, we're going to dive into the science behind our new product platform, Absorv XSE. Part of creating these innovations like Absorb XSE is looking at opportunities to solve past market problems. Transitioning the market to bioresorbable stents from metal definitely isn't a new idea, as many of you know, and it's got a checkered history of trials. Past products mainly focused on the cardiovascular markets. However, those early devices had several key issues. Instead of repeating those, I'm going to focus on how our innovations with the Absorv XSE platform are optimized to mitigate against those issues. New techniques enable optimal molecular orientation and wall thicknesses down to 80 microns. This also allows for higher dimensional and morphological uniformity versus previous generations. Expanded polymer and polymer combinations allow for tailored absorption profiles. These material combinations and optimal orientation and uniformity enable high radial strength and new size options all the way up to 15 millimeter diameters. We may be able to go beyond this later on. This really provides a new product platform with far-reaching possibilities. But let's dig into the science a bit. Here to do that is our senior research engineer, Jay Lindsay. Jay did much of his studies and postgraduate work at Clemson. It's a great place in South Carolina to visit if you haven't been. There, he learned not only material and polymer science, but how to really throw a tailgating event at a college game. Here's Jay.
Thank you, Wayne, and thank you, Laura, for that kind introduction. It's a real privilege for me to introduce to you today a new bioabsorbable tubing platform, one that we are extremely excited about and that we feel is really going to enable a new wave of bioresorbable vascular scaffolds. Like Wayne mentioned, the BRS has really had a checkered history, but really that's been confined to the coronary space. And more recently, we've seen some exciting results in the peripheral space, so certainly is an exciting time to be working on these types of devices. What I'd like to do today is to take a bit of a deep dive into this new tubing platform and really focus on a couple of attributes that we feel will be important differentiators in paving the way for new BRS, not only peripheral, but also in the coronary space. And those attributes are a very high level of dimensional and property uniformity, and as well as tailored molecular orientation. So when we look at the BRS value chain, or ecosystem, if you will, there are a lot of moving parts that designers need to consider when looking to create a successful new device. Beginning with the end in mind, each step in the chain has critical parameters to maximize performance, and our customers often begin the journey with new, unique designs in mind. As you can see, Zeus can help with many of these steps. So not only by selecting or finding ideal combinations of the right materials, think polymers or copolymers or blends, and not only by providing the largest bioresorbable tubing size range on the market, but also, as you'll see later and as we'll focus on in the presentation today, by taking the tubing to really a next level with extremely high levels of uniformity and superior mechanical properties. Next in the chain, we have MeKo, who as our valued partner in precision really plays a major role in taking our tubing to that next level with the precision laser cutting. And again, each step is absolutely critical to meet the needs of new designs. So with our ecosystem as our backdrop, let's dig a little deeper into what differentiates this tubing platform. As you can imagine, producing BRS is all about precision and uniformity at every step. If there's a device category where precision and uniformity are absolutely paramount, it's a vascular stent. I mean, think about it, and especially if it's one that's designed to degrade. So one of the main aspects of uniformity is dimensional uniformity, with most other aspects, such as mechanical property uniformity, really extend from there. So for tubing that's to be converted to a BRS, it's the wall thickness uniformity that's the most important, as there's a direct correlation with strut thickness in the BRS and the wall thickness of the tubing. Wall thickness variation, or we could call it non-uniformity, can rear its ugly head really in two ways, either within cross-section or down the length, or axial, so circumferential or axial. We typically refer to within cross-section variation as concentricity. So if you think about the inner and outer diameter of a tube, think about them as being two circles. It's really that center point of those two circles being misaligned. And what happens there is you end up with a thin wall on one side of the tube. And this can cause a BRS to have a non-uniform radial strength in that circumferential direction. Now, down the length variation can occur when the average wall thickness varies as you move down the length, and that can cause either within scaffold or scaffold to scaffold radial strength variation. And this is really where our new platform shines. If you look at these polarized images on the right there, you can see the major improvements in down the length uniformity with Absorv XSE on the right compared to a previous generation tubing. It's really easy to see in those polarized images. And this really is a game changer. This is something that we are really excited about, and it's going to do really a lot for the markets. So we've seen the importance of dimensional uniformity. Now let's dig a little deeper and look at what's arguably the most important parameter for tubing and BRS design, and that is molecular orientation. So before we dig too deep, let's quickly lay out some groundwork that will help us understand how molecular orientation is utilized in various stent types. Vascular stents, whether they're resorbable or not, typically fall into one of two categories, either self-expanding or balloon expandable, with some key differences. For example, they differ in construction. A self-expanding stent is typically constructed from a braided wire or a fiber, whereas a balloon expandable stent is typically constructed from a laser cut tube. Also, the delivery system is different, or the way that they're delivered, I should say. A self-expanding stent is typically released from a sheath because it has that nice elastic expansion capability, whereas a balloon expandable stent is deployed with a balloon. Also, one of the a very important difference, as we'll discuss later in the two, is the strain level that the stent experiences when it's delivered. So for a braided stent, it's a very low strain level, which stays in the elastic region, and it gives that nice elastic pop out of the sheath. Whereas a balloon expandable stent, the strain level is high because you have very localized strains. And that provides like a plastic deformation, which we'll get into later is by design. And then also, one big difference is the size range available between self-expanding stents and balloon expandable stents. Typically, the self-expanding stents are available in much larger sizes, but however, we really expect that to change with Absorv XSE. As Wayne mentioned, we can get up now to 15 millimeters. So as you can imagine, because of these differences, the components that go into the designs can differ considerably as well, especially when we're considering polymeric BRS. So what we find is that the molecular orientation within the components, that is our biggest lever that we can pull to really enhance the component properties. And then those component properties really feed into the device design, and that's often through an iterative approach, like aided by modeling, like finite element analysis. So in the case of a braided scaffold, it's the molecular orientation within the fiber, and in the case of a laser cut scaffold, it's the molecular orientation within the tube that's paramount. So we've mentioned molecular orientation several times now. So what exactly is molecular orientation, and why is it so important? The easiest way to explain molecular orientation is to take a look at what we call drawn fiber or oriented fiber, which would be suitable for a braided stent. In drawn fiber, the molecular orientation is uniaxial, meaning it's in one direction, and that's in the axial direction or the machine direction. So if you take a look at this simplified schematic of a fiber drawing process, let's go straight to the end there where you see that second inset with the fiber being aligned. This is really what we're after, the alignment or the orientation of the polymer chains. So this is achieved by drawing or stretching the fiber under certain conditions. So if you take a look at that first inset that shows the cone there, what's happening there is as the fiber comes into the oven as shown at different speeds, so it comes in at one speed and it exits at a faster speed, you get an acceleration. And that acceleration has a deformation to it, and then there's a resistance to that deformation which causes stress. And that uniaxial stress ultimately causes uniaxial orientation. And also what can happen there is you get some strain-induced crystallization, which we won't go too much into, but just know that also happens when we orient our tubing. So as a result of this uniaxial orientation, we get a stress-strain curve that looks a lot like this. So it's pretty easy to see why a braided stent would benefit from a uniaxially oriented fiber. Because if you take a look at that blue curve, that's the oriented curve, and it's got a much higher yield strength, it's got the strain hardening behavior, and a much higher ultimate tensile strength. If you contrast that with the red curve there, which is the non-oriented fiber, you see just really subpar properties. But what about a laser cut scaffold? Why would we want to start with an oriented tube? If you consider a typical balloon expandable scaffold design, as we discussed previously, there are regions of high localized strain. So if you take a look at the drawing there, in those red regions, there's a really high strain regions when that stent or scaffold is crimped and deployed, and even when it's implanted in the vessel. So those are regions where the stent has to be very strong and be able to survive that high strain. So now typical absorbable polymers like PLLA or PLC or PLGA, these are very brittle inherently, so they would not survive such high levels of strain. However, if you remember from our drawn fiber discussions, that molecular orientation greatly increases the strength and the toughness of that polymer. So that was going to buy us two things: toughness to prevent fracture at those high strain regions, and two, high strength for high radial force. That way we can have strong scaffolds but with minimal wall thickness. But think about it, there's a problem now, right? All we've discussed so far is uniaxial orientation. And so that would be in the machine direction, which is up and down in our picture there. But the encountered stresses are actually left to right. So in the circumferential direction during that crimping and deployment. So what we really need is orientation left to right or circumferentially. So enter biaxial orientation. So biaxial orientation now is orientation along both the axial axis, or like we've talked about so far with drawn fiber, but now also the circumferential axis. So if you perform a tensile test on dog bone specimens that are cut as shown in the picture there, you have an axial oriented dog bone and a circumferentially oriented dog bone, you will get stress strain curves that look like that on the right. So that blue curve is in the circumferential direction, which shows much higher orientation in that direction, much like the drawn fiber. And the yellow curve shows much lower orientation. And so this particular case, the circumferential orientation really dominates. And that's by design for this particular tube for a certain scaffold. Not all scaffolds would benefit from this, but in this case, it does. So why else might we need biaxial orientation? To explain this concept, we're going to compare and contrast our braided scaffolds with our laser cut scaffolds. So first, back to the braided scaffold. So for a braided scaffold, the molecular orientation within the scaffold, now I want you to think about this three-dimensionally, is dictated solely by the scaffold design, so the braid pattern. So if you consider the green arrow there as that direction of molecular orientation, which of course is uniaxial within the fiber, and the red arrow as the braid angle, they're always going to be parallel. So this is kind of a simple case. But now let's take a look at the laser cut scaffold, where the molecular orientation within the scaffold, so again, think about it three-dimensionally, is controlled by both the scaffold design and now also the biaxial orientation within the tubing. So this is the key. The molecular orientation in the tubing is superimposed onto the scaffold design. In other words, they are completely separate until they are combined when the tubing is cut. So to illustrate this, let's consider the biaxial orientation within the tubing as those green arrows that you see on the left on the tube, and they both have, or the arrows have X and Y components to them, as vectors. So these can be controlled by our process. So we can have more circumferential, we can have more axial, or somewhere in between. So then when the scaffold is cut, of course, these orientation vectors become superimposed onto that scaffold design. So the question becomes, how do we find the ideal matchup between the tubing orientation and the scaffold design? And the answer is, we have to work together, beginning with the end in sight and bringing value at every step. So with Absorv XSE, we're filling this critical role wherein the tubing is ultimately customized to meet the needs of a particular scaffold design. So from a material perspective, a sizing perspective, as well as a custom mechanical properties perspective, these all come together to form that critical component, that beautiful oriented tube that's then ready to be laser cut with precision. And all of this to ultimately enable you as designers to create the next generation of bioresorbable vascular scaffolds. And with that, I'll turn it back over to Wayne.
Thanks, Jay, for those details. Really exciting learnings. Jay discussed a larger range of sizes. So let's take a look at how Absorv XSE is really a product platform oriented to replace metallic stents. As you can see, going up to 15 millimeter allows you to address new potential devices outside of cardiovascular stents. We have many customers now working on novel new designs with the XSE product platform. Some of these designs are already going into human trials. We are seeing new designs from XSE in peripheral, so we will be excited to follow the outcomes as new approaches and designs address areas below the knee. To recap, we've learned today a lot about the science. However, you also have a chance today to make an impact with the knowledge. Absorv XSE is a product platform that represents a new evolution. Precision manufacturing allows ultra-thin and uniform wall thicknesses in a range of sizes to create a host of new device designs. We have prototypes ready, allowing you to begin the journey and help orient the market to replace metallic stents. Stay engaged with us and our marketing partners, MeKo. Together, we can show you new possibilities in precision. Thank you. Now let's hear from Laura at MeKo.
Thank you very much, Wayne and James, for the presentation of uniformity and orientation of Zeus polymer material, which is critical for design success of BRS. This was the first step of the BRS value chain. Now let's hand over to Fridtjof, who's going to explain the capabilities and features of MeKo being able to laser cut scaffolds out of polymer material and a lot more.
Thank you, Laura. Let's take a brief look into the processing chain and the capabilities at MeKo to manufacture bioresorbable scaffolds. It always starts with incoming inspection. The material is unpacked and checked based on its specification. The check can include both dimensional and visual criteria. At least it is checked for the quantity. Afterwards, the material is then professionally stored, for example, cooled and under an earth gas atmosphere. This can be very important to prevent the material from aging. In the most cases, the following step in the processing chain is laser cutting. Here at first, the laser parameters are selected carefully for processing the respective materials, like PLLA, PLC, or whatever. Among many others, the most important parameters are the wavelengths, the laser power, and pulse length. But we will come back to this later. In general, the radiopacity of polymers is extremely low, so that the device is visible to the surgeon during the operation. It is often necessary to include radiopac markers to the device. These are made of materials with very high density and good biocompatibility. The markers are crimped into special designed eyelets, and these are already integrated to the scaffold design special for this purpose. At the end of the process chain, the quality control takes place. There, 100% inspection is performed to ensure conformance with specifications regarding visual and dimensional requirements. The good parts are directly packed here, and depending on which polymer was used, attention has to be paid to whether there are special requirements for the respective material. In addition to the manufacturing processes just described, it is just as important to test the process outcome, the materials itself, and also the performance of the final laser cut scaffold. Some of those testing capabilities we have at MeKo are listed here. Those of course includes mechanical tests as tensile testing using axial and radial laced test specimens. As we already learned from Zeus, oriented polymer tubing is designed to have differences in strength and elongation when we compare the axial to the circumferential direction. The final scaffold can be tested using a radial force testing setup, simulating the crimping behavior into the catheter and the radial force after balloon-assisted expansion and deployment. And this is what you see here in the picture on the right side. Besides those mechanical analyzers, the MeKo MedLab has many testing capabilities for the material itself, like DSC measurement or the measurement of the intrinsic viscosity, which gives an indication of the polymer chain length. And this, for example, is used to show that the laser cutting does not impact the material in a bad manner. As you may already know, MeKo also offers a service of scaffold coating with and without integrated drugs for R&D projects. The coating thickness is, for example, tested with a confocal laser scanning microscopy, while, for example, the concentration of drugs in the coating is evaluated using the high-performance liquid chromatography. Now let's take a deeper look into the laser technology used for BRS manufacturing. The figure below on the left represents a conventional pulse laser technique. Here the laser generates a melt bath, which is then blown out by a directed high-pressure gas beam. This is also a great technique used for highest precision manufacturing, but due to the heat which is introduced to the material, it is not suitable for polymer processing. Instead, for the polymers, you need to use an ultra-short pulse laser system. As the name already says, those lasers have extremely short light pulses compared to conventional lasers. The sketch on the right side shows the shape of a single laser pulse, while the orange line represents the conventional, the green on the green line, the USP laser. And here it is important to say that this is only schematic and it is not a true representation of the ratios. The very high pulse peak power combined with the very short pulse length results in a single laser pulse with an extremely high energy density. And now when a laser pulse hits the material is not melted, it is directly converted from the solid to the gaseous phase. A single laser pulse ablates only a very, very small amount of material. So to cut through the material completely, the repetition rate needs to be very high and is usually in the range of several hundred kilohertz to several megahertz. This means that more than 100,000 pulses per second hits the material to generate a sufficiently large amount of material removal. Besides cutting through the material completely, the USP lasers also can be used to structure surfaces or also to remove coatings in a specific area from the surface. In general, each laser with a pulse length below 10 picoseconds is per definition called ultra-short pulse laser. And characteristic for these systems is already mentioned very high peak power of up to several gigawatt. As a material passes directly from the solid to the gaseous phase, there is not enough time for the energy to be transferred as heat into the base material, which is therefore also called cold ablation. This cold ablation enables us to cut the material without destroying the molecular integrity of the material. The polymer chain length as well as orientation is almost not affected by the process. MeKo performed a case study testing the intrinsic viscosity for the same polymer and before and after laser processing. And we could prove that there is no significant drop of the intrinsic viscosity. Therefore, the length of the polymer chains is not affected. Besides polymers, almost all materials can be processed like metals, ceramics, or even organic materials. At MeKo, femtosecond laser systems are used with pulse lengths down to 190 femtoseconds. The wavelength is adjustable in a range from ultraviolet at around 300 nanometers to infrared at 1050 nanometers. The wavelength must be carefully selected for the respective material. This depends, among other things, on how well the material can absorb the radiation at the certain wavelength. It is also important to mention that some materials can be sensible to special wavelengths like UV light. And this means if you would process UV sensible polymers in this spectrum, the molecular integrity would be destroyed and the material becomes very brittle. In addition to what we have already learned, there are other parameters like focus length and the repetition rate, and all those needs to be taken into account for the specific material to get the perfect result after laser cutting. When we now look at the shape of the cutting slit, this can be triggered during setting up the laser machine. Important parameters here are the focal length and location of the laser focus along the material thickness. The upper figure shows the three extremes triggered by the focus position. In the most applications, the goal is a cutting width that is consistent as possible over the entire material thickness as shown on the right. A lack of material uniformity, like shifting wall thickness or shifting outer diameter, has a bad impact to the cutting accuracy, and the parameters cannot be set with a sufficient precision. An important limiting factor is the ratio between the cutting width and depth, which can be up to 1 to 20. This means for a material thickness of 200 micrometers, the smallest possible cutting width is around 10 microns. If we have a look at processing a polymer tubing, the laser is always aligned to the center of the tube as sketched on the bottom right figure. So the resulting cross-sectional area of the laser cut strut has always a trapezoid shape, and the ratio between inner and outer strut width depends on the tubing geometry. For the best possible result, these parameters must be very well adjusted, which in turn requires high dimensional uniformity and straightness of the tubing. Now let's have a look at some examples from the practice. The picture shows a laser cut scaffold. The material here is Zeus Absorv XSE. The strut width of the horizontal connector is 120 microns and the material thickness was about 110 microns with an outer diameter of 3 millimeters. The scaffold design used here is a very simple generic one, which is used for testing purposes only. The scaffold shown was laser cutted only. Due to the USP laser technique, there is no further process step like deburring or cleaning required. The process itself takes already place in a clean environment to minimize any contaminations. The cutting edge quality and strut width tolerances are the most important aspects to assess the laser cutting quality. And the cutting edge here, as shown, is very clean, and this small black looking edge is caused by the refraction of the light at the edge. The component has almost not seen any heat influence, especially with polymers. This would be directly reflected by a strongly melted or even burned cutting edge. The accuracy here is better than plus minus 10 microns. you can see the strut is very consistent, and this is also significantly influenced by the quality of the tubing. Besides laser cutting of stents, there are many more use cases for USP lasers. One of those is laser drilling of thin layer polymers, which among other applications is used to drill micro holes in balloon catheters. Those drug delivery balloons can, for example, be used for the treatment of stenosis, and the picture on the right shows an SEM photo of a single hole with a diameter of about 6 microns. The drilled diameter is adjustable in steps of 1 micron, while the hole distribution can be adapted to the requirements. And of course, as in the most cases, cylindric balloons are more favorable for processing, but it is also possible to process conical balloons. As we have seen, the material uniformity has a direct impact to the laser cutting accuracy and in the end to the BRS quality. However, another important factor in the production of a BRS is economic efficiency. This is mainly determined by the material utilization, the yield of good parts, and the laser cutting efficiency. To illustrate this, let's have a look at the Zeus Absorv XSE, which is roughly twice as long as tubes of previous generations. And this longer length enables a higher level of automation because the laser machine is loaded manually for each tube, and then the laser automatically cuts a certain number of scaffold until the material is used. This means for a doubled tube length, the operator needs to intervene half as often. Moreover, each tube is fixed in a die, and so there always is a certain tube length that just cannot be processed. This waste is of course minimized. Nevertheless, a longer tube length results in less waste and more components to be cut from the same amount of tubing. To show what can be achieved for the BRS by using tubing with improved dimensional uniformity and straightness, MeKo performed in a collaboration with Zeus a study testing the Absorv XSE against previous generation polymer tubing. Therefore, 30 scaffolds each have been produced using same cutting pattern, laser machine, and so on. The scaffolds then have been tested in the MeKo MedLab for strut thickness, which is shown on the left scaffold, which is shown on the left, and the thickness in the middle, and radius strength consistency on the right. The strut thickness is directly linked to the wall thickness of the tubing, while the scaffold mass in combination is a combination of wall thickness and strut width consistency. The latter is determined by the laser cutting. Each of the test results shows significant improvements and demonstrates the benefit for the device. Special attention should be paid to the results of the scaffold radial strength consistency. This demonstrates very well that if great material uniformity and very high precision laser cutting comes together, bioresorbable scaffolds with much more predictable performance will be the outcome. Finally, I would like to take a look at the engagement of material and the manufacturing processes to show what needs to be taken into account for BRS development. The process steps have been broken down here to the design of the BRS, the material, laser parameter set, marker crimping, coating, and the sterilization procedure. Each of those have its significant impact to the final device performance. The crimp and expansion behavior, for example, is of course a very important feature for the BRS, and this is tremendously determined by the design itself, which needs to match perfectly with the material used. Zeus' capability to trigger the molecular orientation really brings advantage here and has the potential to take the BRS to the next level. However, the theoretically best design is useless if it is not realized with the required precision. So the laser cutting needs to be done with highest accuracy, especially for scaffolds with very thin struts, for example, of 100 microns or below. Even an accuracy of plus minus 10 microns means a fluctuation of 10% in the strut width. Up to this point, the scaffold is not visible for the surgeon during the operation, and therefore markers can be inserted. The size depends on the density of the material used, and the location of the markers must be taken into account in the design planning already. For example, the marker eyelet should better be located in an area that is not severely deformed during crimping or expansion of the device. And frequently used marker materials are gold, platinum or tantalum, as those materials have a very high density and also a good biocompatibility. Particularly for the biopolymers is the shelf life of the material and the finished BRS. And the shelf life is directly determined, among other things, by the base material selected, but also the laser cutting or the storage can have an impact here, as well as the coating and the sterilization process. Finally, we have the resorption rate, which is probably one of the most important features for a BRS. This is for sure determined by the chosen material, but also influenced by the design itself. In general, the bigger the cross-sectional area of a single strut is, the longer it takes. And besides the design and the material, the resorption rate can be slightly influenced by the coating. In the end, of course, it also depends heavily on where the device is implanted. As we now have seen, all these steps have an influence to the performance of the finished component and must be carefully selected and executed to the highest standards to get the perfect performing next-gen BRS.
This part concludes our webinar. If you did not send your questions yet, please write them down in the questions area. You can also send us an email or contact us on LinkedIn or other possible channels. I would like to thank all our speakers, Wayne, James and Fridtjof, and everyone for joining us today. The video will be available on our homepage and on YouTube. We hope to hear from you soon again. Have a great day.